Hello and welcome to Solving the Climate Materials Bottlenecks, a webinar on assisting climate positive materials integrating themselves into value chains. We're going to speak a little bit about how you can start to commercialize technologies. Instead of taking 9 years, we're going to condense that down to five and maybe even two. So, to start out with, who are we? I'm Dr. Jason Tobias Deacon. I have a PhD in material science from the University of Cambridge, and I've spent around about 7 years in the industry trying to commercialize and successfully commercializing technologies from Tier 1 to Tier 9. And we'll go more in depth into what that means later. And joining me, not here today, but part of the team and leading the AI and materials development is KV Petty. And so we'll start out nice and simple for those who don't have a materials background. What is a materials property? It can be considered a skill that a material has, a skill required for a certain job. So let's start easy. Steel has a high density, has a high yield strength, and a low flexibility. When we go a little bit more complicated, we can speak about the metal organic framework 74, magnesium, has a certain specific surface area, high specific surface area, a moderately good CO2 absorption, and a certain pore size. These are all skill sets that the material has and what gives it a special property. Now, let's speak about the market pull. This is kind of the job that is requiring that material skill to certain have to fulfill and succeed. We'll start easy. Steel versus cardboard. The yield strength, the strength of cardboard is around about 4 megapascals, whereas steel can be anywhere between 250 to 2500. That huge difference is the reason why we don't want to build buildings out of cardboard, not ones that last anyway. But let's go a little bit more complicated. If we compare MOF 74 versus aqueous monoethylamine, they both have different specific surface areas, but they're both very good at sequestering CO2 or capturing CO2 in flue gas. The difference there is the environment. You can think about this as even though an electrician has brilliant skills and perfect for the job, if the environment is, for instance, underwater or they're, doing a civil servant architecture job, then the skills and the environment aren't really well suited. And so you have to think about things like input method, technological maturity, instability in water, these other environmental properties. And if you go even harder, we can compare biochar and coke. So biochar and coke are both carbonaceous materials, and they can both be used in green steel to create green steel. The issue is that during the manufacturing of green steel, there's a transport belt that carries the coke to the green steel to be deposited. And used in biochar, it has this property where it's a little bit more fluffy, so it kind of flies off the conveyor belt. And that's a culmination of where the environment isn't specifically seen. Yes, in the intermediate case, we can see certain material properties that we can test and analyze. But when we're talking about specific industries that use a conveyor belt to create their steel, then that's where it gets a lot harder, a lot more difficult to predict. And so it's a very complex issue. You have these culminations of regulations, processes, properties, applications, customer requirements. And normally, teams are around about 2 to 5 people. Over the course of 2 years, 2 to 5 people in these climate positive materials based companies. They have a limited capital and they have limited resources, be that human or working capital. And generally, commercialization, it takes around about 9 years, 9 years for a quick commercialization. 20 years is around about the standard, and it can take up to 40 years to reach true commercialization. It's a huge, complex issue, but it can be solved. And so let's take a little step back and really simplify the process down. Let's look at what a value chain is. A value chain has an end customer who requires a certain product, be it a material product like a shirt or some kind of memento, a building perhaps. And then the downstream supplier creates that product. They create that shirt. Then a midstream supplier is responsible for transporting the materials required to make that shirt. And then the raw material, be it cotton, linen, is created somewhere else. As you can see that the linen gets transported to the manufacturer who makes the product. And there's a lot of groups involved in that. So the end consumer pays the downstream who pays more up the stream. So the flow of material goes from the end consumer to the upstream, and the flow of material goes from the upstream to the end consumer. And this is a very simple example. There's obviously lots of branching value chains and multiple partners. Value chains are core to what we're going to be solving today. And so let's talk about inserting yourself into these value chains. Once you have a product, that is the most important thing to get into a value chain. If you are the entire value chain, then you're making something for yourself and yourself is going to buy it. It doesn't make sense. There's so many players in a value chain. You need to integrate yourself into one or create a value chain around your product. So we'll talk about a simple way to get involved in the value chain, which is low risk and low capital. And that is a drop-in solution. So let's say that there's a steel industry that needs more high demand of iron, and therefore you're an iron producer. You produce your iron through green methods. You can quickly integrate yourself into that value chain because of the demand. There's a market pull, we say, for your product. Now let's talk about medium risk and medium capital. You have a byproduct. For instance, during the pyrolysis of hydrogen, you can produce a carbon byproduct, the steam methane reforming. You can produce a carbon byproduct which can be integrated into the steel value chain, but it might not have the specific skill set yet. For instance, the purity might be too low or something like that. And therefore, you invest the capital there to work on improving and getting that material which is skill adjacent or job adjacent to make it perfect for that material. So integrating it that way is medium risk. Alongside, you're not set up to fully manufacture this material there, right? So you have to involve a few more capital to get invested in that value chain. I'll talk about steel because steel is a common example, but this can be applied to any product at all, any material product. If you're looking into flue gas and want to sequester CO2 from there, if you're looking into structural engineering and things like that. So it can literally be applied to any product on this earth. And so let's talk about the most disruptive one as well. So disruptive value chains, such as artificial intelligence, is higher risk, high capital. And so it requires a lot of money to get involved in the value chain or to start creating these value chains. And it can be a high risk because of the expense of it. And it is high risk because you're creating entirely new value chains around you that integrate into your value chain. And often there are players that are getting removed. So you're removing the incumbent, you're upgrading systems that might not necessarily need to be upgraded. People might have to buy equipment to get involved with you. And that is the core thing about creating a disruptive value chain. Graphene itself creates a disruptive value chain, and AI is an example of this. So, when you have a market pull, you have the end consumer, there's a need, there's a desire for a certain product. Does your material fit the job? The moment you have that desire is the moment you go on what we call the technology readiness scale. So it's a scale between 1 and 9, but we'll talk about the most important aspects of it. The idea, the moment someone says to you, we want this, you have an idea, I can fix that for you, I can fix that problem. We'll take, for instance, the sequestration of CO2 in flue gas, which is mandated by the government to be reduced in emissions. So, firstly, someone has an idea. MOF 74, I believe, works, and therefore they make MOF 74. And then they show a proof of concept in the lab. They've moved from TRL 1 to TRL 4. They've demonstrated that MOF 74 has the skills that are required, aka that it does absorb CO2. And then from 4 to 7, you start testing it in an operational environment. You partner up with organizations and say, can we coat this inner tube of your flue gas with MOF 74 and test the CO2 coming out of it to show that we have removed some of it? And you start to grab these pilots, you start to validate it in an operational setting. And then you reach full commercialization. You've proved that it works and you've manufactured it, you've scaled up to the point where it's relevant. There are many, many pitfalls in that, but that's a nice way to organize and manage risk. And this was invented by NASA in around about the 70s. Okay, so valleys of death. This is the reason why a lot of technologies don't reach commercialization. So the first valley of death is normally supported by the government, and that is in an academic laboratory, and there's a technological valley of death, which means the skills of the MOF 74 or steel don't meet the end requirement. So you wouldn't really use steel as we know it today to sequester CO2. Therefore, there's a technological valley of death. But MOF 74 does, and therefore it can cross that valley of death. And once you hit level 4, You are now open into the lab scale, and now you can start doing production and prototyping, as we said before. And now we start doing the commercialization of Valley of Death. Are you able to produce MOF 74 in the purity that you require, at the manufacturing standards that you require, and able to partner with people who will use your product? If the mandate comes in 2050 that they must reduce CO2, and we're currently in 2025, then there might be a lack of adoption of the product. But if it's in 2030, and then that kind of speeds up the adoption of the product. And that's how you cross the second valley of death. And finally, we reach TRL9 and onwards, where you look at the profitability valley of death. If it costs you $1,000 to produce 1 gram of MOF 74, then it's not really profitable because there's CO2 removals. There's going to be other technologies that are more viable there for you. So these pits and valleys of death are what really stop commercialization of climate technologies from reaching their full potential. And so we break this down into a few problems. The scientific deficiencies. A team of 3 scientific leaders cannot read thousands of papers in, say, 3 months. There's often cases where they have done their PhD around this topic and they know pretty much all of it, but there are some missing key factors. It might be something like the equipment used to scale up is now advanced. It might be other things such as financial requirements. It might be aspects like it doesn't sequester enough carbon. There's certain technical deficiencies that can lead to the plummeting into the value of death in ones, two, and three. Remember, that was the technological, the commercialization, and the profitability of it. Second problem is that there's partial understanding of the market needs. Some people make it and hope that they will come. If you fully understand your customer, you can have a customer from day one and say, great, you're at tier 1, I'm your customer from day one. If you make up to tier 9, we will buy it from you. As long as it hits these criteria, you have a nice set of metrics you can hit in order to meet your customer demand. So being green isn't just good enough. You need to add value. If you have a high fire resistance for your material, but then you're working in something that just gives you a green product, you can use that high fire resistance, and that's where you're adding value. Thirdly, collaborations are required to set up value chains. I've said before, you're not alone in this. You're not the only person, not the only company getting involved in this kind of technology. You can connect with industrial researchers, government researchers, public researchers, and other communities around you to help start either integrating into the value chain, understanding it, or creating your very own value chain. There's so many players around your technology. So the solution is agentic AI in 4 key methods. We developed a materials passport. True North Materials has developed a materials passport, which is essentially an advisor. When you're at tier 2 and you need to get to tier 3, what do you need? What services are available at you, and who can kind of help you verify that? It's kind of like going through the gates, which is why we're calling it a materials passport. The market agent is a market analyst that truly finds product fit. The process agent is your own individual scientist that condenses down literature into scientific and business related outcomes, which is truly important. And we'll speak more about that later. And then there's a collaboration agent, which acts as your business developer for the value chain and the ecosystem. AI and agentic AI, especially, are at the point now in history where we can do hyper personalization of the company, and hardware is no longer hard. The materials passport is the center. We talk about this gate based approach. TRL4 to TRL5, what do you need to reach that next hurdle? This is a great way to also speak the same language. It's a great communication layer. The sales team can speak to the business team, can speak to the materials team, and truly know where exactly the product is and what are the capabilities. Everyone understands the skill set of the material. And I say that because communications can sometimes be difficult between people of different vernacular and different terminologies. The business believes that they are at tier 7, the technical believe that they're at tier 4 and just have a proof of concept, and the sales are already selling it like it's tier 9 and already commercializing it. It's just in our nature. But with a materials passport, you can ask someone, an AI that is grounded in your information and say, where are we? What are the steps? Can I do this? Can I sell to this partner? No, you can't, because their manufacturing needs require 100 kilograms per day, and you are currently at 5 grams per day. That's a huge distinction. And it's a communication layer for all of it. And having that set of going from 4 to 5 is crucially important because that opens up many opportunities for you. And this integrates advisors into the matrix. You have company advisors who can verify that you have moved from 4 to 5. And it also helps you with your due diligence. All the documents and the reasoning of why you're at tier 4 or tier 5 or tier 7 is stored in the material's passport. So human approved, and it shows a great communication layer of how to get through these gates. Next is the market agent. So you have these certain skills. Your material has inherent intrinsic properties, these skill sets. Where can you find a market that would be great for your material? Where can you find your product fit? And this analyst goes from very, very general, such as understanding a certain plastics market, until a very automotive market, and then digging deeper and deeper and deeper until you find a specific company that has the right ESGs and the right goals as you and is a perfect fit. Many of the times, finding what this is called a beachhead client. Finding that beachhead into the value chain is the most important thing. If you can find one person to purchase your product, then you can start getting the ball rolling and suddenly you're connected to that value chain and you have revenue. This 2 year, 9 year, 40 year commercialization, the moment you get that revenue is a huge milestone and it should be the most important thing that you aim for. The science, everything is devolved around that. And like I say, the moment you have that market pull is the moment you start at TRL1 and the moment you start your journey to commercialization. And it gives you a North Star towards where you need to go. And it is grounded in internal data for your product. So it knows everything about the product. It knows everything about the business's needs, certain capital that you have, the goal of yours, and it finds you the ideal product market fit to help you hit those beachhead clients. Finally, the process agent, which is how do I get the material skill? Maybe you find a market that you really want to get involved in and it has a high growth rate, but your material is just not there. Maybe the purity isn't there, maybe the thermal resistance isn't there. The process agent shows you how you can get from property A to property A plus or property A upgraded. And it shows you, given a certain angle, I want to get from here to there. And it's evidence backed. It scours thousands upon thousands of literature and even offers exchangeables. So now CEOs can ask CTOs and technical staff, I noticed that we're using a weak base here. We're using sodium carbonate. Why don't we use potassium carbonate, for instance? Because it might be cheaper and things of that nature. So it's enabling and improving the scientific team, which remember is around about 2 to 5 people, and whilst projecting business-related inquiries. So the CEO can be fully informed, the business team can be fully informed of the bill of materials and estimated price and how to get to that end goal. Finally, the collaboration agent. So each step on the TRL scale, from 1 to 3, 4 to 7, opportunities open up for you. The moment you hit TRL 4, TRL 5, NSERC opens up. Your ability to collaborate with a research partner at a government institution, say the Advanced Materials Research Facility. You now at TRL 4, that opportunity is open up to you. Say you're at TRL 7, TRL 9. Now that you're there, NGen and Scale Out and other opportunities, non-dilutive funding consortiums start to open up for you and really push your product from here to skyrocket. These are the core to advancing advanced climate technologies. You establishing that value chain and understanding who is there to support you and how you can help other people is the most, it's incredible when you can think, I didn't know I had this kind of help available. And it can just be as simple as that chat at a conference. It could be as simple as having a discovery call with someone. And then I've seen it where businesses, entire relationships, entire trajectory are based on that single conversation. It doesn't have to be like that. Of course, it's fantastic when that happens. But when you get matched with someone who is perfect for you, that's better than having 100 market discovery calls. And so, in summary, the problem of partial understanding of market needs is solved with a personalized market analysis. The scientific deficiencies have a personalized scientist that scans, a collaboration agent that acts as your personal business developer. And therefore, you have the market pull for the value chain. You understand the end consumer's needs. You understand the technology required to enter the value chain. And you understand the people involved to get involved in that value chain. It's an augmentation process. So, in summary, you can finally be attached to a value chain that is climate ready. Thank you very much. I'm Dr. Jason Tobias Deacon. My LinkedIn is on the screen, and I welcome you to add me and let's chat further. Thank you.